Video number 22 plus, Newtonian black holes. Hello everybody. There has been some excitement about black holes in the last few years, either to say that we have photographed them, or exactly some phenomena associated with their presence, because a black hole is invisible, or to say that they don't exist, or to say that the entire universe lies inside a giant black hole. This kind of turbulence is normal concerning objects whose very theory says that they are invisible. But less obvious may be the link that is almost always done with general relativity, as if black holes could only be explained within that framework. Black holes were considered long before relativity. It was indeed already possible to imagine them within Isaac Newton's theory of gravitation, based on the corpuscular theory of light of the same Newton, since one could assume that the grains of light, later called photons, have a mass. This is how John Michell in 1783, then Laplace in 1796, both realized that if a spherically symmetric body is sufficiently dense, any photon which approaches it is trapped by gravity. In the framework of the classical Newtonian mechanics, the gravitational field produced by a spherically symmetric mass distribution coincides outside the heavy ball with the field that would be produced if all the mass were at the center. See about this a video entitled Newton's Incredible Luck. From there, we calculate in a classical way, by an argument of energy conservation, the minimum value of the velocity, independent of the mass, and called escape velocity, allowing an object which takes off from the surface to go to infinity. Where the escape velocity exceeds that of light, no light can be emitted far from the region now called the Schwarzschild sphere. It is this property that defines a black hole. After these fundamental historical reminders, let's see in more detail how black holes can be conceived within the framework of the so-called classical Newtonian mechanics. Let us therefore assume a spherically symmetric mass distribution contained in a ball of radius small r and see the effect of gravity on a quasi-point particle of mass small m, located at the distance capital R greater than small r from the center of the ball, and having a velocity v at instant t, which can be taken as the origin of time. The total energy of the particle is capital E equal 1/2 of mv squared minus capital G, capital M, small m over r. If the particle can go to infinity, it implies that capital E is non-negative, since at infinity the potential energy is zero, and the kinetic energy is positive by definition. We therefore have capital G, capital M, small m over capital R less than or equal to 1/2 of mv squared, which simplified to v squared greater than or equal to 2 capital G, capital M over R. In the case of the photon, we have small v equal c, the velocity of light in empty space, and therefore, under the opposite hypothesis, 2 capital G, capital M over capital R greater than c squared, all light starting inside the sphere of radius capital R is confined. The value Rs equal 2 capital G, capital M over c squared is called the Schwarzschild radius. It is a precise value below which the escape velocity becomes larger than c for a given total mass capital M. At least that's what is written in Wikipedia, and this is summarized in the drawing describing a possible thought path by extrapolation from the terrestrial escape velocity. Actually, we can proceed further. If we consider the case of an outgoing photon emitted at the time t0 following the normal to the ball of radius capital R, the equation of motion governing the distance small u of the photon from the center u double prime equal minus capital G capital M over u square shows that near t0 the speed v equal u prime is decreasing. We can therefore see that Newtonian mechanics applied to the photon is incompatible with the propagation of photons at constant speed. On the other hand, admitting a possible decrease in the speed of photons, a simple calculation shows that if capital R smaller than 2 capital G capital M over c square, we have norm of u of t less than or equal to capital R divided by 1 minus c square over 2 capital G capital M capital R. The condition small r smaller than 2 capital G capital M over c square characterizes black holes. It says that if the radius is very small compared to the mass, that is, if the mass is very concentrated, the spherical object behaves like a black hole. It is interesting to translate this condition in terms of average density in the ball of radius small r. Indeed, it is generally said that the density of matter inside a black hole is very high, and we invoke a singularity in the center. In reality, the presence of a singularity is not necessary, and we will see that the density of a black hole can be very low if the radius small r is very large. The average density of the spherical object of radius small r is small d equal capital M divided by capital V, with capital V equal 4/3 of pi r cube. So small d equal 2 over 4 pi capital M divided by r cube. We obtain the inequality d greater than k divided by small r square, with k equal 3 over 8 pi c2 over capital G. This last inequality can be considered as a characterization of black holes in terms of the radius of the heavy zone and of the average density. And we then realize that no matter the average density, above a certain radius, we are in the presence of a black hole. What happens if we test this inequality on the observable universe? We can verify that k is approximately equal to 1.61 10 to the power 26 kilogram per meter. Knowing the observable radius, which is approximately equal to 4 times 10 to the power 26 meters, we deduce that k over r square is approximately equal to 1.61 divided by 16 times 10 to the power minus 26 kilogram per cubic meter, very close to 10 to the power minus 27. However, the density of the observable universe is presently about this value. From this point of view, those who think that we live inside a black hole may not be completely wrong, especially since the radius of our universe is supposed to be much larger. The problem is that it would be a black hole for outside observers, assuming there's a lot of vacuum around it, so it doesn't make so much sense. On the other hand, if in some region the average density overpasses 10 to the power minus 27 by a large factor, which is easy to achieve, the region being surrounded by vacuum or immersed in an area of very low average density, this may produce a huge black hole. More elaborate calculations also show that spherical symmetry is not necessary for this to happen. A link to the corresponding paper is available in the description. This could mean that the matter contained in some gigantic areas of the cosmos is invisible for us, especially since the peripheral luminous phenomena that signal the presence of very dense black holes could be absent in the case of low density. At the end of this discussion, three things appear. Point 1. Perhaps the speed of light should be interpreted as that of the light wave and not that of the photon. Point 2. Gigantic black holes of very low average density are conceivable. Their matter could influence the global dynamics of the cosmos and would constitute a category of dark matter, probably not very different from the ordinary matter that we know. Point 3. Incidentally, the existence of such giant black holes could provide a new alternative solution to the Olbers paradox.